All right, thank you. Are you guys ready? All right. So, good morning, everyone. My name is Ethan, and this is the wonderful GHGT Robotics team. Just to give you a little bit of what we are about. So, the GHGT Robotics team's goal is to provide education to the youth of Hamilton about robotics through workshops and just mentoring programs. So, today, our team is here to present to you is IceCube. Yes. Our product today is IceCube. You're probably wondering what happened to our light hazing drone that was in the booklet that was provided to you at the conference. Well, about a week ago, about a week ago, we were recalibrating the flight of the drone, and due to a malfunction in the end, the drone crashed on its side on a very hard pavement floor. So the frame was completely done, and we were all sad. We worked so hard, and then this had to happen, and it was a terrible moment. But you know what? We all stuck together, and in a week's time, we came up with this cute little robot called IceCube. So here's a picture on the screen. Ice to the power of 3 because we like math. So what is the function of IceCube? Well, in bare bones, its function is to follow a path that is drawn on our computer screen with a mouse. You might be wondering how it works. My friend Vinay over here is going to go into a couple of details, trying to explain to you guys how it works.
So what do you get? We've got a SumoBot, Raspberry Pi, an Arduino, a lot of brains, a webcam, and a computer. You got this IceCube. So it's a real hack job. We did it in about a week. So the Raspberry Pi receives information, sends it to the Arduino, and the Arduino acts on the motors. And then the motion is sensed by this webcam over here. And then the correction is made on the computer. And then we have that feedback loop that you can see over there. And if everything goes correctly, it should follow our movements as we tell it to.
Right. So the reason we chose the Raspberry Pi and Arduino was because we found that through a lot of testing that the Raspberry Pi would receive information wirelessly and package it and send it to the Arduino in a very efficient way. The Raspberry Pi also has really good Wi-Fi capabilities, as when you buy the Raspberry board, it comes with the Wi-Fi abilities already ready to work with it. So we found out that the Raspberry Pi was a very important and useful part to this robot. Right, so what are the benefits of IceCube over here? Well, the first benefit is that it is extremely feasible. So this robot costed us about $280 to build. So what this would help when manufacturing is that it would cut down costs immensely. Let's say a company takes this and releases it to the market and mass produces it. That $280 will be cut down immensely because you can cut deals with suppliers for materials. You can cut deals with the laborers, as it is also easy to build as well. So you don't need highly technical ability people to build this robot. Because it is so easy to build, since we did it in about a week, this will also help when you are, let's say, giving it to a student or an elementary high school student, as they can easily put it together themselves with an easy-to-read instruction manual. Another benefit of the IceCube is that it is very small and portable. In today's world, we are always moving fast, traveling here and there. You know, we live in an age where technology needs to be portable. And this is one thing we try to incorporate in IceCube, and that it's small and portable to carry anywhere you go, to carry to any terrain, to test it, or just to have a fun time with it in different environments. The very last benefit is that it comes with a very easy, user-friendly software, which you basically just have to, I'm going to show you a slide, two slides before. Okay, right here. You can't really see it on the screen due to the lighting, but this software, all you have to do is draw the path on the user interface on the computer itself, and IceCube here will follow that exact path right to the dot. All right, so now I'm going to talk about the applications that IceCube can be used for. Right, so the first application that we thought that the IceCube could be very useful for is agriculture. So let's say you are a farmer and you want to harvest or you want to plant seeds. You can easily draw the path of your crop field on the user interface, and IceCube here will follow the path, and it could drop seeds or even be used on a bigger system to harvest crops. This will also reduce costs for the farmers as they don't have to hire workers to farm their fields. There we go.
Yes, in the second applications, this algorithm can also use for the civil construction. For example, before building the gardens, this robot can sketch a nice layout on the ground so that the garden can be built accurately by following the children's path. This is one of the applications of larger scale drawing. Also, I think there are many things can be done by attaching different tools on the robots. For example, on the art purposes, I think people can simply drawing the pictures on the tablets or maybe a laptop so that the robots can draw nice pictures on the grounds and well, maybe on the big papers. This is also one of the most amazing features of our robot.
Right. And the very third application that we see that IceCube here can provide is it can provide a very good base for research. The Arduino and the Raspberry are very easy to code and to test your code on as well to see if your thesis or any kind of results that you're trying to prove or implement. It can also help in automobile research when it comes to safety testing, as you don't want people in the car as you're driving them towards each other or towards a wall. So you can always implement this system in a car and just send it in the direction you want and test maybe airbags, suspensions, or many different things. So the very last application that we thought that IceCube could be useful for is robot education. Now we think that robot education is a very vital part to the students and children of this age, because we can see that in the world right now, there's more of a technological advancement happening. So it's key for us to understand what's happening in the technological world in order for us to progress with our problems in the world, such as global warming, problems with like droughts, things like that. So all these issues around the world we see that the solution is technology that's going to help us. Right. And also, as GHGT, found that using the Raspberry Pi and the Arduino, it's very easy to communicate to high school students or to elementary school students the basic fundamentals of programming, and implementing this with sensors or motors to actually gain some kind of movement or direction any sort of way. So we feel like this is a really good teaching tool as a whole to teach to students. The Wi-Fi capabilities is also good for students to understand how networks work, how clients work, how UDP, TCP works in the environment that we all are in right now. So okay, so in conclusion, we started off with a drone that didn't work out. Okay, we had a week left. All we had were a couple of parts remaining. We didn't have time, so it just goes to show you that with what little you have, you can make something really great and useful if you just think outside the box. And that's what we have brought here with IceCube. The IceCube is shown to be feasible. It's shown to be easy to use. It's shown to be it's portable as well. And we felt like with the time constraints that we were sadly drawn upon, we came up with a very innovative product that will be easy to commercialize as well. So now we're just going to do a quick demo to show you guys how the software works. and then we'll take your questions. Thanks.
Yeah, go ahead.
Okay, so do you guys see, can you see it? Yeah? Okay, so the red X is what Zach is controlling, and the white X is a Kalmar filter. Basically, it's just a filter that just tries to go towards the red X. And you can see that wherever he moves it, it's going to follow the path, and this is what the robot should follow.
Yeah, press the button on top.
I just restarted the server.
Yeah, the communication is through the Wi-Fi, and we got the router at that side of the room. So maybe if there's some interface, so we didn't get it at the first time.
But you can clearly see how, without any feedback control, it's pretty pointless. What we've tried to do with the light painting was actually use the image recognition when we had the quadricopter, but our quadricopter died. So I was like, okay, why don't we just make it look down? So that's what we did with the new code.
So we got a camera hanging up there.
And you can see the cameras over there.
Yeah.
And track the image. Go. Do the signs. There we go. So this is going to track the image. And where's my, yep, there's my cursor. Here we go. We're going to start this. It's going to be a lot of fun. Now, one of the things that we didn't anticipate is that on a quadricopter, you don't really have an angle. Come back. You can do it. I believe in you. But on a robot, you do have an angle. And it's very difficult to get the angle without more vision control. This was designed for the quadricopter, but it still works. Go with that. Should
Yeah,
go for the
if
red
you
eye.
look at the screen, you can see a green dot. The algorithm for this is like it takes two images, and then compare with it to see which part is moving.
Right, so thank
And-
you for listening.
Yeah, basically can track anything if you stand in the front of the camera.
Put a hand in there.
Yep.
Face, anything. Do we have any questions?
Thank you very much, guys. Questions for the team? Any questions? So this was part of a drone, the control system that you developed was for drones?
Yeah, it's for a flying drone. So we had to convert it to a ground.
And
drone
what
system.
changes did you have to make to convert it for a ground system?
Well, in the drone, you just have the X and Y, right? You don't have an angle. You don't have, because this thing, it can't really go this way. It has to go that way.
I see. Okay.
But in a drone, that doesn't really happen. So you could just map it wherever you wanted to. But being an adaptable system, like the image processing that we did, we were able to quickly adapt it. It was done yesterday.
It does the same function as the drone, but simply for the path.
Yeah.
But again, remember, as much of an importance of in a robotics is not just the hardware, is also the software. So your software to control is something you guys wrote yourself?
Yes.
Okay.
It was all done with open source stuff, with OpenCV, Arduino's open source, it was Raspberry Pi. Yeah.
So in the beginning, you said that building a slow machine like the ice cube would be much costly. And in your innovation, you mentioned the cornfield or like the like farmer's field. But for the fact that you need a camera on the top, how much more would that cost, and like how much would it save to get the camera on top?
Well, we already have, aerial photography and photographs and things like that, right?
I mean,
Have you considered the drone and this working together? So you have a drone up there.
Yeah, we can have the drone to holding the camera to give feedback, and then you can have the truck going in the field, and you just draw the path on your tablet to move around.
Yeah, one of the biggest aspects I thought of when we were designing this was, suppose say you were a SWAT team that wanted to cover your plane, you would put a quadricopter or a drone up in the air, and then you could physically map out, okay, Ice Cube, go this way, and then it will cover your plane, waiting for the bad guy to come in and get blocked off. There are many aspects that you can use to use pathfinding. I'm pretty sure you guys know a lot about this stuff. Dr. Barfoot probably does a lot of that. But the main idea is not having a robot that is basically controlled by a human, but having a robot that has a sense of intelligence that could still function on its own without human input. And the only human input is for strategic decisions, not simply go here, do this, go here, do that, go here, do this. Because that's not really sustainable in your lives. I think human-robot symbiosis is much more prevalent, and it's much more needed in the future compared to simply from what I got from this.
One more question.
I was just curious if you considered doing like close proximity horizontal plane like laser distancing, and then of course with the farmer's field application you can integrate like a GPS signal at some point, like for a larger application. But in close proximity, you could just have omnidirectional laser distancing, and instead of the camera from above.
Well, that's a design choice, right? We didn't really have a LiDAR.
No, I got you.
And the great thing about this is that you could build it with a box of scraps and a couple of hundreds of dollars. That's the idea behind this. It's rapid prototyping with result platform.
Well, one of the things that we haven't had, and maybe teams would consider, we haven't had two robots collaborating together in any of our competition, but that's the trend now. It's not just robot and man, sometimes robot and robot collaborated to complete a task. So it'd be great to see this with your copter, and then see whether the two of them can collaborate to do something. Anyway, well done. Congratulations. Thank you. Okay, well, this team sort of answered. Our next team is Beaverworks from Our Lady of Lourdes Catholic Secondary School in Guelph.
Good morning, everyone. So today we're here to talk to you about our robot, Polar Vortex. We are from FRC Team Beaverworks. My name's Mayer, this is Relly, and that's Henry over there. And today we're going to introduce you to our awesome robot. Alright, so the first thing I want to talk to you about is our capabilities. So while we were prototyping this robot, we had three things in mind. The first was simple operation and movement. The second was a good ball retrieval system. And the final thing was a good ball release system. Next one. All right, so first we have our operation and movement. Now, as you can guess, a key component of movement is the ability to drive. That's why our drive system is probably the most important thing. So we chose the hexagonal base this year as opposed to the common rectangular base, and there were many reasons behind that. But the most important reason was that we chose what is known as a holonomic drive, which uses what are called omni wheels. Now, if you look in the picture on the bottom right, you'll see that it looks almost like a regular wheel, except that it also has perpendicular rollers on it, which allows it to move forwards and sideways. So we have 6 of these wheels on our robot, 1 on each side, and each of those are powered by their own motor so that we can send an individual speed to each motor, and in the result, having different speeds on each motor sends a different direction to the robot. And if we need to rotate, we can send it with rotation if required. And the second part of our operation and movement system is the field-oriented control. So essentially what that means is the robot has no front or back. Now I know that might sound confusing, so I'll start off small. On there we have this chip which is known as a gyroscope, and that tracks the angle of the robot. Now, when our operator is controlling the robot with a joystick, the software receives an angle from the gyroscope, and so the outputs from the joystick are adjusted accordingly. What this means is that the operator can control the robot based on his or her surroundings. So let's say we were facing like this, and we wanted to drive forward. The operator would push their joystick forward, and it would move forward. But if we rotated right in a regular robot, and then we drove forward again, the robot would actually move this way. However, in this system, if the robot is rotated right, and we still move forward, the robot will also move forward. So it all depends on the operator's point of view.
The second point for our, that we had in mind when we were prototyping was ball retrieval. Now, how we achieve this with our robot is using a retrieval arm. The retrieval arm uses a linear actuator and other mechanisms that essentially allow it to change its geometry to be able to pick up the ball and reach out in conjunction with the rollers attached to it to suck the ball in and also be able to release it outwards. Another thing that we had in mind was the ball release. Now, with the ball release, we had a mechanism called a cam actuated release mechanism. So essentially what it is it's a gear system that allows for a continuous drive for ball release. And how that works is, how that applies to us is that it makes it very simple and very, it essentially makes it simple and intuitive in that it only moves in one direction so that we don't have to retract it every single time by reversing direction, and makes it easier to code. We also use limit switches, and we have a physical limit so that it doesn't, it provides a safety aspect to it so that it doesn't fire automatically. You actually have to push a secondary button as well as the fire button so that no one can accidentally fire it by mistake.
Alright, so we're gonna be showing our demonstration right now of the holonomic drive, the launching mechanism, and the
Ball retrieval system.
ball retrieval system. So how the holonomic drive works is that it allows you to move in any direction without turning the actual robot with the 6 omnidirectional wheels. So as you can see that I am moving forward. As I turn the robot to the side, I am still able to move back and forward without having to move the robot back into its front position. Right? So how this works is that the gyroscope on top of the robot tells it or gives it a sense of direction according to the user's point of view instead of the robot's point of view. So in this case, we're able to move front and back without having the robot turn, move side to side, and having the robot rotate. Another good example of how a robot moves with our point of view is we're able to move back and forth while spinning, also side to side. Another thing on our robot is the ball retrieval system. So
The arm moving back, and you have the arm moving forward, and then we have the launcher. So back to the limit switch. If I hold down this button, it'll winch the launcher, but it won't go anymore until I hold down the other button. And the reason for this is so that there's no misfire. So if somebody is in there when they're not supposed to be, the launcher won't launch. So Henry drives towards the ball. The arm goes down, and the rollers can roll the ball in.
so you're gonna launch it.
Okay. And then to launch the ball,
So similar to what the previous FRC team said, this was created for the competition, and as you can see, it is able to do all of the tasks that it was.
all right. So if we look at the picture that's on the screen, that's what I was talking about before, where you have individual powers in each motor. Somebody wants to come up with this. So I'm not sure if you guys can see this, but if Henry drives it forward, you can see that only some wheels are spinning and the other wheels aren't spinning. So what this does is it causes the robot to move in one direction. So you can see that these two wheels are stopped and these ones are spinning, which would cause the robot to move forward.
And you can see how in this case the power is distributed differently, and these wheels sometimes spin slower in relation to which direction you see going.
And rotating, if you rotate it, they'll all go in the same direction. But see, they're all spinning in one direction. See, they're all rotating in one direction. All right, so now to apply this robot to the real world. So there's many ways that this robot could be applied, but what can mostly be applied is the unique drive system. It's intuitive, it's adaptable, and the controls are very easy. In fact, we toured many schools while we were in the FRC season, and we had grade 4 students driving this around for the first time. Very well. So some of the ways we could use these systems, for example, are wheelchairs. So I remember one time I saw somebody in a wheelchair. We were in the grocery store, and it was a really narrow aisle, and they had to turn around because they closed off the aisle on the other end. So they had to make a 3-point turn inside the aisle, and that could be very cumbersome for a lot of people. But what if you could just rotate on the spot and turn around? Wouldn't that make life so much easier? I think it would. Secondly, we have forklifts. Forklifts are also vehicles that are very hard to drive, and you have to make 3-point turns with them. So if we could rotate on the spot or just move left and right without having to turn at all, that would make it a lot easier for the drivers. Next, we have autonomous operation. So let's say we pre-program this robot to go somewhere, for example, a maze. So with a regular robot, when you're programming it, you have to take into account that it's pivoted And then you have to figure out, okay, now I want it to go forward, but really that's right. But with this, you can get it to maintain the same orientation, but it'll still move left and right. So it makes it a lot easier for the programmers. Also, another feature is the gyroscope would help with self-correcting drive. So if you were to get it to go straight and the gyroscope sensed that its angle was drifting, it would be able to correct the robot so that it would move back in a straight line. And finally, personal robots, such as the Roomba. If your Roomba could strafe and not have to turn, it would clean your house a lot better. And that's why I think they should implement a holonomic drive system.
So, so previously the Roomba uses the old system of driving, so it has to turn. In this case, it would just be able to move laterally instead of turning in a three-point turn fashion.
And that is it. Do we have any questions?
Well done, guys. As you see, we have a number of these competition, and for this specific, we are looking at some, as you said, some of the components which has gone into design elements of it, and not necessarily for how far you can throw the ball. And your drive system, you said, is quite unique in its ability. The wheelchair application is obviously of great interest to people. Why do you think they haven't used this?
To be honest, I think one of the...
By the way, do you know Hamilton has the highest number of motorized wheelchair any city in Canada per capita? So you're in the right home to commercialize this. For some reason, we are the home of motorized wheelchairs.
Well, I think one of the reasons they haven't implemented it is just the fact that it's a change from the standard wheelchairs that we know today, where you have the joystick and you're turning around. But I think once they would be introduced to this type of thing, it would be useful. Also, the other thing with holonomic wheels is sometimes the rollers don't actually have grip, so it might be a little bit harder for you to drive around. But I think with the right adjustments to the wheel, it would be able to work.
Any other questions?
Those wheels are quite unique. Are they commercially available, obviously?
Yes.
So they're in other applications, some.
But they're mostly used for the first competitions and robotics competitions.
Yes. Go ahead.
I have a question about like the forward momentum. Like, do you get less speed or torque when you go forward versus like when you put it on the spot?
So yes, that is the case. So when you're going forward, you'll go to about 70 or 80%. But what we have it as on the joystick is it actually multiplies that value so that you go up to 100%. So you're not going as fast, but you are using as much of your motor capacity as possible.
Great. Thank you very much, guys. Well done. Okay, our next group, and they can start to set up while the Beaverworks group come off, is Kinetic Knights from the Kincardine District Secondary School in Kincardine.
the Kinetic Knights. We are a FIRST team along with the other 4 teams here. We are in the FRC, which stands for First Robotics Competition. FIRST is an acronym for Inspiration and Recognition of Science and Technology. So they're kind of going for the same thing that this conference is trying to do. And there are about 2,720 FRC teams in the entire world, and there are a few here today.
Our team consists of about 45 students aged from grade 9 to 5th year, along with 15 mentors, all contributing to building the robot, programming the robot, wiring the robot, and also organizing the team.
Our team was founded in 2002, and to present day, of course. Some great achievements we've had is in 2002, our rookie year, we won the first Canadian regional ever in Canada. And then our next greatest achievement would be in 2011, we went to the World Championships and got second in the world.
Use the mic, please.
And we got second in the world for it. Along the way, we also had multiple achievements winning regionals, and in the past couple of years at the GTR East Regional, we've won the Chairman's Award, which is the most prestigious award you can win in FIRST.
If you look towards the screen, you'll see right where we're from. We're from a small town called Kincardine. It's on the shore of Lake Huron, and a fun fact is there's no other robotics team or FRC team within 125 kilometers of us.
So, the 4 people that are here today, I am Gregory Reed. I am the build captain for next season.
I am Matthew Strader. I am the design strategy for next season.
I'm Vraj Tripathi, and I'm the programmer.
And I'm Chris Pierce. I'm the mechanical lead.
So, like the other teams have already said, this game was called Aerial Assist, which our robot was designed and played for. I'm just going to do another run by quickly. Aerial Assist is played with a 2-foot exercise ball, which as you can see here. The match actually starts with a 10-second autonomous period, where the robots move around autonomously trying to score as much points as they can. After those 10 seconds, a teleop period starts, where teams can try to pass around the balls or bonus points, shoot a ball over a truss, and you can catch, if the robot is designed to catch, and shoot it into 2 different goals, a high goal and a low goal. The match is about 2 minutes and 30 seconds.
So the robot that we designed for the 2014 game, we call it Big Bruce 13, which we also nicknamed Moose because of the antlers. Our speed is ranged from about 6 to 18 feet per second. We have a max pushing force that we tested of about 250 pounds. Our control system is a National Instruments C-Rio, and a 12-volt lead-acid battery powers this beast.
So the design process that we went through to design this robot began with getting the game animation, which first puts out on the first Saturday of every January. So we get this explanation of the game, and from that we decide the best way of scoring points. So we analyze the game, and then once we figure out a strategy that we want to go with, we create our scope for this season. And right here, this is our scope. So ranked 0 is driving. 0 is the base of every robot we've made. So we've figured out that it should be 0. Every robot should do it. That's how important it is to us. And we know that we can do it. And then ranked first for this robot was passing the ball, because if you can pass the ball, you should be able to pick up the ball. And if you can do those things, you can give the ball to your teammates, which can give you the assist points. And that means you can contribute to your team without worrying about the complexity of shooting the ball. And assist points also allow you to seed higher in the competition.
Coming at number 2, we've got shooting. And to be honest, who doesn't want to see a 2-foot ball flying through the air? so we decided we want to shoot. Shooting is also a really great way to score points other than passing. And passing is also important because the game is called aerial assist. By shooting, you can score points. There's a high goal and a low goal. We decided to go for the high goal because it can get you 10 points while a low goal gives you 1 point. So we decided it would be possible for us to make a really accurate shooter, and that is exactly what we did. Now, for catching the ball, it is one of the more complex things that one of the robots can do, and it gives you 10 extra points. A full cycle without catching gives you 50 points, and a full cycle with catching gives you 60 points. But it also takes some time because you have to align the robots, shoot, and then another robot will catch it. We decided that without using this time, we could actually fit in more cycles and therefore get more points.
So some continuous improvements we've done to the robot, as you can see, is our intakes. When we first started with the intakes, we actually had a motor driven with a chain and sprocket, which didn't seem like, it wasn't as effective compared to our new pneumatics. They always got jammed in our old sides, which are now aluminum with Lexan side panels on them. And they're very slow and not as efficient to pick up the ball. And like I said, the side panels we changed out from PVC piping, which are now aluminum, like I said. We added motor mounts to them, which help aid bringing the ball, which are mounted to a bag motor. It's driving a 2-inch wheel, which is a Banebot. So this helps get the position of the ball inside the catapult, ready for shot.
The next improvement we made was the sensor for the ball. Our sensor used to be a proximity sensor located close to the tower of the robot. This didn't give us accurate results, so we decided to change it and innovate to put a light sensor out farther away from the tower. The reasoning for this will be explained later.
Another obstacle that we found during the season was at one of our competitions, we had a high-speed impact with another robot. When this happened, 3 of our welds broke on our tower. So when this happened, we realized we would have to take anything plastic or anything that could melt all of our electronics away from the points we were welding, because if we left them there, from the heat of the welding, they would all melt, damaging all of our electronics. Our electronics were very close to what we had to weld. So lucky for us, our electrical panel is quite easy to remove. So we were able to move the electrical panel, cover everything up, and we welded our robot back together at that competition.
These are some of our innovative components. These are some unique and unconventional ways that we use parts on a robot that worked very well. The first one is a ratcheting wrench. Normally you would see this in any other shop. It's used to tighten nuts and bolts. But what we used is we used it on a mechanism called the choo-choo to help it from the catapult arm sliding back up into the top position you see right here, so we wouldn't have to keep driving it back down, wasting time and energy. But with the ratcheting wrench, since it can only go one way, there's no way for the catapult arm to slide back up.
Another innovative component that we decided to use is these Bombardier snowmobile spring suspension springs. So these are the torsion springs, and the way we use them instead was to tension the catapult so we can shoot the ball for maximum points into the high goal. Very simple to use.
The next pieces we used were hockey sticks, or the antlers. Being a Canadian team, we had to use hockey sticks on our robot. It's become a tradition for our team to use these. Uses for these are playing hockey, road or ice, and some people just use these for recreational use or training. The reason we use these is because these curves are equal and there's a slight toe curve. This makes the ball very easily cradled and the ball stays secure. We have had these on almost every robot so far.
The next component that we really like is the grip tape on the rollers. It's called Safety Walk. You'll find this on boats or stairs or any surface that could be slippery at a point. So it gives you more grip if you need it on the ground, but we used it to give us more grip on the ball, because without the safety walk, it would have been just bare conduit against the Pilates ball, which wouldn't have brought in the ball as effective as with tape.
Now for our innovative systems. These aren't just singular parts that are pretty unique. These are systems as a whole which made us more effective. For our catapult sensors, like I said before, we used to have a proximity sensor by the tower, and now we have a light sensor farther away from the tower. The reasoning for this, for the distance change, is because when an arm moves, you'll see that the radius over here is different. The circumference from a circle starting here is different from a circumference over here. By doing this, a centimeter over here is harder to read than 10 centimeters over here. It's easier for a sensor to pick up a change of 10 or 20 centimeters than to pick up a change of 1 or 2 centimeters. By doing this, we got more accurate results, and this way, our robot always knew when the ball was down and the catapult was armed. By doing this, we wouldn't have as many misfires.
Another component that I mentioned earlier was the electrical panel. So it connects to a frame with 10 1032 bolts. These are all into 8th aluminum, so they're really quick to pull out. So once you get those 10 bolts removed, all of the wires connecting to the motors are connectors either crimped on or connected to the wire very easily that you can just pull the wires apart. So very simply, you can take the entire electrical panel off of the robot. This is good for situations where you need to fix the robot without the electrical panel, or you want to look at the electrical panel just by itself without having to fit into tight spaces in the robot. What's also good about the robot is, or the electrical panel, is that it's made on an insulated base of Lexan. So you won't have a massive short between two of your control systems. They're completely isolated, so you don't need to worry about those shorts. And all of the electrical is on one base, so we were actually able to build the robot and the electrical panel, like the mechanical parts of the robot and the electrical panel simultaneously, and then one day put them together and then wire the robot, and then we would have our full robot. So we didn't have to build the robot, then do electrical. It was all at the same time, which saved us a lot of time.
Our next innovative system is a mechanism called the choo-choo, which I mentioned earlier. It is used to pull down the arm, the catapult arm, and arm it ready to fire. It is a very compact and powerful machine that is very reliable and durable due to its fact that it is made mostly of 1/4-inch aluminum along with two heavy-duty steel gears with a gear ratio of 233:1. The choo-choo is powered by a mini-sim along with a planetary gearbox, and it also has a safety release pin just in case the arm is armed, and all you have to do is pull out the pin, pull a bolt out, and slowly release the arm back up to its normal position so you don't have to dry fire and have the possibility of breaking something.
And the last innovative system that we have is part of our drive. So I'm not sure if you can get a good look at it, but we used our chain actually inside our chassis to help us save space. So usually people have it on the inside where the electrical panel would be or where the wheels would be. But in the past, when we've always done it, it would always cause us a lot of time in the pits. That's where we work on the robot competition. Trying to replace the wheels if they need to be retreaded or if we have a pop tire. Where here, all we have to do is take off the bumpers, take out a bolt with a hub, and the wheel just comes simply right off, not having to worry about the chain or sprocket. It takes a 10-minute job and turns into like a 5 or 3-minute job. Very easy.
Now for some of our innovative software. Our robot has encoders for the drive. This helps us a lot in autonomous mode. The software has changed it so it converts it from rotations to inches. So when we're deciding for autonomous mode, we can tell the robot, we can measure and see that we want the robot to move, say we want it to move 4 inches, and then it'll convert it, and then the robot will do what it needs to do to move those 4 inches. Another thing is we have safeties for our catapult. The system is so it'll pull it down, and then once it's down, all the gear needs to do is turn an extra 1/8, and that'll launch the catapult. But no one wants to sit there and watch the robot and time it, so they have to let go. So we have 2 different buttons. One button will pull the gear down, or pull the arm down by rotating the gear. But when it gets to a certain point, the sensor will pick it up, and it'll stop. And if you press that button anymore, it won't do anything. But a different button we have will turn it that extra 1/8 of a rotation and launch the catapult. By doing this, we don't have any fires when we don't want them to. We have many buttons on our joysticks, for our controller joysticks. The drive joysticks only have a shifting button, and that makes it so the driver doesn't have to focus on too many things at once except for driving. The operator who works on the joystick you can see right here on in the back has a variety of buttons that control almost every separate feature on the robot, and then easy to reach buttons for systems that are activated. The systems are like intake, outtake, shoot, and things like that. But in case of any jams, there are buttons for separate key components, which you can fix any jams. We also have a consistent autonomous code. As stated before, autonomous is a period of time before a match where drivers are not allowed to touch their joysticks, and the robot does whatever it needs to do, scores points, and those give you more points. We have a consistent 2-ball autonomous with a 1 hot goal. A hot goal is when an autonomous, there are 2 goals in a game, 2 high goals in a game. In autonomous mode, one of these will be randomly lit up. Our robot can look at these and shoot there and get us extra 5 points.
You guys want to show your robot work?
Yeah,
we're going to do that.
with the demonstration afterwards.
So now we'll quickly move on to the real-world application of our robot. So looking at this robot, you probably won't see an application for throwing a 2-foot ball around a hospital or a warehouse. But if you take it apart and look at the systems that we used, you can see that you can apply them very easily to robots around the world. So there's easy to remove components, like the wheels that we talked about. We're able to replace a wheel and the hub in less than 5 minutes. And we can take the electrical panel out, completely remove it very quickly also.
Another one would be saving space. So a way that we save space is, like I said, putting the chain inside the chassis. Gives us a lot of room for electrical and for mechanical jobs. Another one would be mounting our motor controllers, which are called talons, on top of our gearboxes, which are the flashing lights as you see down there. And that saves, like again, a lot of space for us.
Another real-world application is our robot's very powerful pushing ability. That's due to the fact that it has very large pneumatic wheels, along with a very fast but powerful low gear. So we tested this out on 2 of our previous robots by pushing both of them sideways on carpet, which is quite a feat. You can use this in a real-world application in like any factory or workplace where loads are either too heavy or too dangerous for any average person to push around, and the robot can just push it to wherever you want it to be.
Thanks for listening to our presentation. Now we'll give you a short demonstration to show how this magic actually works.
All right, so they'll just quickly get the joysticks set up the way they need them, and then we'll quickly run through all of the systems on our robot. So those Lexan sides are quite easily removed, so we can look at an electrical panel or maintain stuff very easily. It's just Velcro. So it's also able to spin on the middle axis. It has that's the powerful low gear, fast, and that is able to push 250 pounds very easily. There's the choo-choo running, if you can see inside. So that's the grippy rollers, and the wheels able to quickly bring it into the robot. So it can usually fire much further than that. We just took the extra tensioners off of the torsion springs. It could usually fire about 25 feet. So pardon? No. Yeah. Not really. So that's our robot right there. I guess if you have any questions, you can ask them.
Hold on, guys.
I have a question. Yes. Kincardine is very close to the Bruce nuclear plant. Yeah. And I noticed Bruce Power is on the side as one of the sponsors. Have you discussed an application with them? I mean, I wouldn't want to be tossing uranium sticks around. But it seems to me that there could be an application in a plant of that size.
Well, an application that this could have is if there's some place where you don't want humans to go and move stuff. Yeah. This actually has a very strong pushing force. To clarify, we actually pushed two of our robots sideways together. So they were side by side, and we were able to push them both while they're on carpet. So they're gripping the carpet, and we were able to easily push them. So if you have a pretty heavy crate or something that needs to be pushed across and it has radioactive material, you can actually just use a robot instead of a human. And it might be too heavy for them as well.
So is that a yes or a no? Have you discussed an application?
We haven't talked to Bruce Power about that specific application, no.
Get on it.
Any other question? Great, thank you very much. Well done, guys. Okay, our final group are from the Humberview Secondary School in Bolton, and the Alpha Dogs.
Us, the Alpha Dogs.
Not the most creative name, I'll admit, but it works. So, as the other first teams have explained, the robots are designed to play in the game that First releases to us each year. So every year it's a completely different game, but it's generally on like a typical 50-foot by 25-foot field. So every year you do a completely different game, and you only have 6 weeks to work on the robot before you can't touch it, and you have to just leave it as it is. This year we are playing with a large 2-foot diameter exercise ball, where the main, as you can see in this image, the main goal is to throw that large ball up into a high goal. But the other main aspect that First added this year, which hasn't been seen before, is working with your other teammates. The way to get the most points, other than just scoring, is passing back and forth between your teammates, throwing over the truss and having your teammate catch it, collaborating, which is something really exciting because you don't know who your teammates are going to be, so you kind of have to make a versatile robot to try to work with all the teams you see.
Working with our game and at 6 weeks build times, we had to really innovate with the kind of materials we have, especially